So yesterday we took a look at some applications of exponential functions, and I said the word some because it's impossible to cover every single application of exponential functions. Likewise, 4.7 will just be talking about some ways we can use logarithmic functions. Um, Now, understanding when to use what type is sort of pretty easy. The idea is this: if you notice a phenomenon of something that's increasing or decreasing, radioactive decay, population growth, so on and so forth, that is increasing or decreasing proportional to its current value, the more stuff you have, the faster it goes, that is an exponential situation. Logs, on the other hand, are typically used when you're dealing with really, 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 really big or really, 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 really small numbers. That is why you typically see logs used in the natural sciences, like, astronomy, distances between planets. Those are really big values, so they'll use a log scale. In chemistry, when you're talking about, the weights and the size of electrons and protons, that's a really small number. You might typically use a log scale. So we're only going to talk about a handful of applications just so you get the feel for things, get your feet wet, of a specific application of logs. The first being a pH scale. Right? If you've taken chemistry, or heck, even watched a TV show or movie involving chemistry, no doubt they've tossed in the word pH just to make it sound fancy. What it is it's a way to describe the acidity of a solution. Now, before the 20th century, chemists basically described the acidity of a solution by the amount of hydrogen ion in the solution, the concentration of it. And for the most part, this was okay. But when it comes to acids and whatnot, we're still talking about a very small amount, like 0.0001 moles or 0.00005 moles. And you know what? Working with all those decimals and negative exponents was a pain in the butt. So in about the turn of the century, 1909-ish, I think, a chemist by the name of Soren Per Lort Sorensen just said, you know what, let's stick it inside of a log, because logs make really, really small numbers into nice, neat numbers. So instead of dealing with, 0.00001, chemists now dealt with numbers like 4 and 4.2 and 5. But I digress. You don't really need to know all that information. You just need to know how to use it. So what is the pH scale? It says the pH of a substance is equal to the negative log, and that's the common log, of the hydrogen ion concentration. That's it. Easy peasy. It doesn't get any more complicated than that. Let's go ahead and define this, just in case you look back at your notes and going, what the heck does this mean? So this symbol, bracket H plus, is the concentration of hydrogen ion measured in moles per liter. Now the idea is that 7 is sort of your baseline. If your pH equals 7, we call the solution neutral. If pH is bigger than 7, we call the solution basic. And the exact opposite, if it's less than 7, we call the solution acidic. And this should make sense, because the idea is, at least in this definition of an acid, what makes a solution as an acid is a substance that sort of strips away electrons from an object. So if you were to dip your hand in acid, why does it burn? Why does it melt your flesh off? It's because the hydrogen ions are literally stealing your electrons away from you. So the more hydrogen ions you have, which would mean the smaller the negative exponents, that would translate to a smaller log value, hence more acidic. Again, you don't really need to know all the science behind it. Basically, pH of 7, neutral; pH greater than 7, basic; less than 7, acidic. That's all you need to know. I think what we'll do is we'll just write down all the scales first, and then we'll do some example problems later. So, what's another situation, another context at which we can use the logarithmic scale? Well, we use log scales a lot when we're talking about earthquakes, right? So, we have something called the Richter scale. Of course, named after the geologist Charles Richter, who found a way to map or sort of compare the magnitudes of earthquakes. And it's very, very simple, right? So it's all these log formulas are simple, I think. So by definition, the magnitude of an earthquake is equal to the common log of I over S, right? Where this capital I is the intensity of the earthquake. Now, the intensity of an earthquake is measured by the amplitude of a seismograph reading taken 100 kilometers away from the epicenter. So, have you guys seen those, in the movies where you see this machine and it's just going up and down, and then when there's an earthquake, it goes up really crazy? That's a seismograph. So, what geologists do is they sort of measure the peaks and valley, how long those squiggle lines are, and that's how they get the magnitude of an earthquake. Right. Now, S is the intensity of a, quote, standard earthquake, if I can spell earthquake. Now, unless you're going to go into like seismology or studying earthquakes, for our purposes, we're going to stick to it as 10 to the negative 4, right? So S is going to be a constant, call it 10 to the negative 4. What other things we can use logs for? Well, we can use logs to measure the loudness or the intensity of sounds, right? So we have something called the decibel scale. And much like the Richter scale, it follows the same idea. So the decibels of a source of sound is equal to the log, common log, of the ratio of I over I sub naught. Again, where I is the intensity level of an object, and I sub naught is sort of like your standard intensity. So all of these scales, the Richter scale, the decibel scale, it's always measuring against what scientists deem as, quote, standard. Again, if you're not studying this for our purposes, all you need to know is that the I sub naught will always be 10 to the negative 12s. And if you're interested in the units, it's watts per meter squared. So it's the amount of wattage for every square area. So those are just a few applications of logarithmic scales. Solving problems involving them, it's just like what you did in 4.6. It's knowing which scale to use, plugging in the information they give you, and then solving for whatever it is you're asked to solve for. So let's just go through several examples, maybe at least one or two of each type. Say, for example, the hydrogen concentration or hydrogen ion concentration of a sample of human blood was measured to be H plus equals 3.16 times 10 to the negative 8 moles per liter. Find the pH. And classify. So clearly, again, not on the test, I'm not going to tell you, hey guys, this is a pH question. Hey, this is a Richter scale earthquake question. Just like how I'm not going to tell you, hey, this is an exponential growth problem. Hey, this is a radioactive decay problem. But I think it's pretty obvious. It's talking about hydrogen concentration. It's talking about pH. Of course, we're going to use the pH scale. So the first thing I'm going to do is write down the formula. pH equals negative log H plus, and then just plug in everything they give you. Well, clearly they gave you H plus, so you just plug it in. Like I said, these problems are very anticlimactic. You just figure out what formula to use, plug in the information, and then just do math. Right. So you go ahead, pop that guy into your calculator. You're going to get a pH of roughly 7.5. Okay. Now it's time to classify. Since the pH is slightly bigger than 7, we know that any pH that's bigger than 7 will be basic. So I would say, slightly neutral or basic. Right? It's not far off 7 where I can say it's not neutral, but it's somewhere in between neutral or basic. Right? Easy peasy. Since this formula only uses two variables, there's not a lot of different things I can ask you. So here we said to find the pH, we can go the opposite direction. I'll give you the pH. Suppose I asked you find the hydrogen ion concentration of a solution with a pH of, I don't know, I'm just making this up, say 2.4, right? It's a very acidic solution. Well, again, clearly it's a pH problem, so here is our formula, negative log of H plus. They give you 2.4, which is a pH, so you just plug into the pH spot. 2.4 equals negative log of H plus. And then you just go ahead and solve for H plus, right? So this is just a log equation. First thing I want to do is get the log by itself. So let's divide both sides by negative to get rid of it on the right-hand side. And then to get rid of a log, we will exponentiate to base 10. So there we go. H plus is equal to 10 to the negative 2.4. And you go ahead and pop that guy into the calculator. You're going to get about 0.00398 moles per liter. Now, if you want to be fancy and all, scientific, we can convert this into a scientific notation number. That's 1, 2, 3 spaces, which is 3.98 times 10 to the negative 3 moles, right? So, if you want to be fancy. Let's do some earthquake examples. So, examples here. Let's say I ask you to find the magnitude of an earthquake that has an intensity of 3.75. Again, remember, intensity is just sort of the height of the squiggles on the seismograph. So this earthquake caused a squiggle that went up 3.75 centimeters on the seismograph. Well, gee whiz, it's talking about earthquakes, so probably we're talking about the Richter scale. So the Richter scale magnitude is equal to the common log of, I believe it was I over S. Now remember, S is always 10 to the negative 4, so we don't have to worry about that. What information do they give us? They give us 3.75, which is an intensity. So just plug that guy in. You're done. It's that simple. Log of 3.75. And again, S is always 10 to the negative 4. Pop that guy into your calculator. That's about 4.57. So that's when you hear like news report. Oh, it was an earthquake, a category, or no, those are hurricanes. Like an earthquake, the magnitude of 5 or magnitude 8 earthquake. That's what they're talking about. It's sort of the ratio of the intensity to the standard. Let's do another example. Say Now, this example that I'm getting it from uses place names, San Francisco, Ecuador. I'm being lazy. I'll just call it Earthquake 1 and Earthquake 2, right? Let's see here. Oh. Earthquake number 1 had a magnitude of 8.3 on the Richter scale. Proper noun. Earthquake 2 had an earthquake 4 times as intense. What was the magnitude of earthquake 2? Again, I'm being very lazy here. I'm going to abbreviate earthquake as EQ. Now, the reason why I chose this example is a common mistake students make is they sort of confuse magnitude with intensity, and please don't do that. Let's take a look at the Richter scale. I guess I can rewrite it here. Magnitude equals log intensity over 10 to the negative 4, right? Intensity is inside the log, and magnitude is outside. So just please be careful with that. So if you read the story, earthquake 1, they gave us a magnitude. All right. Earthquake number 2, it says it's 4 times as intense. So the information we got for earthquake number 2 is an intensity, not a magnitude. But somehow I'm supposed to use that information to figure out the magnitude of earthquake 2. So this is what you do. You basically have to write down what information you're given. So let's write down what information we're given. So clearly we're given information about 2 different earthquakes, the yellow and the pink. So I'm going to write them down separately. So we know for earthquake number 1, they gave us a magnitude, 8.3 equals log. They did not give us an intensity, so that's I over 10 to the negative 4. We know for earthquake number 2, we do not know his magnitude, so that's an M equals log, but we do know his intensity. It's 4 times as intense as earthquake 1. Now, if we take a look at earthquake 1 here, his intensity, even though we don't know it, is I. So the pink here, up here, says it's 4 times as intense. Well, if intensity is I, how do I write down 4 times as intense? It was not meant to be a trick question. It literally is 4 times as much. So 4I over 10 to the negative 4. Now, how am I supposed to evaluate this? I still have variables here. Well, here's the cool thing. We can do a little bit of properties of log, little trickery here. I know that a single log of I over 10 to the negative 4 is 8.3. That's what this equation says. So all I have to do is make the inside of a log look like I over 10 minus 4. In other words, I have to split apart the 4 and the I. Fortunately, we have properties of logs. We know that if these guys are timesing each other, I can split them apart in their own separate logs with addition. So this equals, the 4 will get its own log, plus, and I want to keep this guy here together, so I'll keep them together, log of I over 10 to the negative 4. Now you're probably going, well, why would you want to do that? That makes things look more messy, look more complicated. Well, what does, let's see, what color can I'll just use this here. What does this guy equal? Isn't he the same as this guy? Sure, and he equals 8.3. So there we go, we're done. Log of 4 plus, I know that whole guy is 8.3. Now, of course, log of 4, you'd have to take out your calculator, push some buttons. You're going to get that this is approximately 8.9. So an earthquake that was 8.3 on the Richter scale, if you have an earthquake that is 4 times as intense, it only bumps up to an 8.9. But you can see how these logarithmic scales work. It allows you to take big things, because when you multiply by 4, it tends to get big, and chart them on a relatively smaller scale. So an 8.9 versus an 8.3 doesn't sound like a big difference, but indeed it is. Let's do one last example here. So let's say you have a third earthquake, right? Earthquake number 3 had a magnitude of 7.1. How many times more intense was earthquake number 1 from the previous example? How many more times intense was earthquake number 1 than earthquake number 3? Okay. So basically, what this question is asking you is, hey, compare the intensity of this earthquake to this earthquake here. Just so I'm not scrolling back and forth, let's just go ahead and summarize what we know. So earthquake number 1 had a magnitude of 8.3. Earthquake number 3 had a magnitude of 7.1. And I want to know how many times more intense this guy was compared to this guy. Gee, how in the world are we going to do that? Well, what we need to do is sort of build, or sort of see if we can't write down exactly what we want. I want to compare how many more times intense the intensity of earthquake number 1 was compared to number 3. Do you guys agree? That's basically saying I want the intensity of number 1 as compared to the intensity of number 3. That's what I want. And this guy should equal some number, right? Call it x. That should equal some number. Well, what I could do is we could do this. We could find these guys separately. Remember how the magnitude equals log of intensity over 10 to the negative 4? Well, they gave us the magnitude of them each. So we could just use this formula twice to solve for I and then divide out our answers. I think that's an easier route to go. So let's go ahead and do that. So let's do the earthquake number 1. So for earthquake number 1, we know 8.3 is equal to the log of the intensity of earthquake number 1 divided by 10 to the negative 4. So this is solving a log equation. So let's exponentiate both sides to base 10. So we get 10 to the 8.3 equals I sub 1 of 10 to the negative 4, and then go ahead and multiply both sides by 10 to the negative 4. So we get I sub 1 equals 10 to the 8.3 times 10 to the negative 4. I'm actually not going to use my calculator. I'm going to use properties of exponents that says when I multiply bases, you add the exponents, 10 to the 4.3. I want to keep things as exact as possible so I don't get any rounding errors. So there we go. We got the intensity of earthquake number 1. Let's do the same thing for earthquake number 3. So earthquake number 3, we have a magnitude of 7.1. So 7.1 equals log of intensity of number 3 over 10 to the negative 4. And repeat the process. Exponentiate with base 10. You get 10 to the 7.1 equals I sub 3 of 10 to the negative 4. Multiply both sides by 10 to the negative 4. Properties of exponents. You get 10 to the, 3.1. So now we can answer our question. What is it that we want? We want to know how many more times as intense earthquake number 1 was to earthquake number 3. So you just do earthquake intensity number 1 divided by intensity of earthquake number 3. So that is 10 to the 4.3 as we found out from above, divided by 10 to the 3.1 as we found out down here. And of course, properties of exponents, you subtract them. Oops, that's a 1.2. So there we go. It's 10 to the 1.2 times as intense, or pop that into your calculator, 15.85. So I know that earthquake number 1 was 15, almost 16 times as intense as earthquake number 3. So some of these problems, yeah, you might have to play around with the formulas, but I promise you, you just got to practice and get better at it. But any time you have a problem that involves earthquakes, it's just the Richter scale formula. Last, let's just do a handful, maybe 1 or 2 examples of the decibel system. Let's go ahead and do a quick example here. These ones aren't as, we can do since the decibel system is just as similar as the Richter scale system, we might be asked to do the same questions. Suppose I ask you to find find the decibel level of a jet engine at takeoff if the intensity was measured at 100 watts per meter squared. So clearly this is talking about noise, it's talking about sound, it's talking about decibels. So we'll use the decibel formula. The decibel formula is B equals 10 log I over the standard, which is 10 to negative 12. Actually, I think I made a mistake here. I don't think I put the 10 at the very beginning. Whoops. Nope, I did not. Haha, little mistake there. So let me fix this really quickly. Decibel is B equals 10 log of I over I sub naught. All right, got to make a note of that later. All right, that 10 is important because it's a decibel. Deci means 10. Well, figure out what information they gave you. They gave you 100 watts per meter squared. That clearly is the intensity. Pop that into the intensity. Boom, you're done, right? So again, more anticlimactic stuff, but pretty simple, I hope. Oops. 10 to negative 12. Right. And then just pop that into your calculator, do some math, and you're going to get 140 decibels. Right. And of course, I could give you the decibels and ask you to solve for the intensity. So I think you guys get the idea. Clearly, I'm making mistakes here, so I should probably wrap up this video and get some sleep. But that's it. That's how you find, that's just some applications of logs, pH scale, Richter scale, and the decibel scale. How about it? Good luck.